ಏನಾಗಿದೆ?
Sir? Yes, sir.
ಏನ್ ಫುಲ್ ಬ್ಯುಸಿ ಆಗಿದ್ದೀರಾ?
No, sir.
ಏನ್ ನಾವು ಆ ಟಾಪಿಕ್ ಕವರ್ ಮಾಡಿದ್ವು ಏನು?
ಸರ್ ಅದು ಸ್ಟಾರ್ಟ್ ಮಾಡಬೇಕಿತ್ತು ಸರ್ ಇದು.
ಓದಿದಾ?
ಹಾಂ ಸರ್.
ಜನರೆಲ್ಲ ಕೇಳಿದಾಗ ಹೇಳಕ್ಕಾಗಲ್ಲಪ್ಪ ಯಾರುವೆ. Okay, now let me start from this slide. If I have not covered. Okay. So in the previous class, we discussed about the analog links, how your electrical signal is converted, and all those things, sources, indicators in the previous chapter. So here, analog link we studied, wherein we discussed many noise that was added at each stages, maybe at the transmitter side, or maybe in the channel side, or in the detector side, that is a destination side, or during at the destination side, whenever we amplify the signal, because the signals what we get out of the fiber, it will be very less in sense, it will be having very low, the signal gets faded, so it will be having very low signal. So in order to get the original signal, we will be modifying it. Modifying it means that we'll be amplifying that, and then we'll be sending it out. Okay. So there we discussed so many noises, that is harmonic, RIN, model distortion, ASC, and short noise, thermal noise, all these things, right? So in the previous class we discussed about this carrier to noise ratio, that is signal to noise ratio nowadays. Earlier it was carrier to noise ratio. Then later on we studied about carrier power, carrier power. Then later on, we discussed about the photodetector and pre-amplifier noises that is given by general some equations. Then after that, we discussed about now we are about to discuss about the relative intensity noise. So what is this relative intensity noise? Relative intensity noise. So as you all know, whenever the in a lasers, in the, that is a semiconductor lasers, there will be variation, or there will be fluctuation in the intensity or phase, sorry, or the frequency. See, frequency at the output of the output, right? So there, even though when the laser will be biased at a constant current, we will be uh, what will be coming out, or we get signals with the variations in the variation in the fluctuation in the intensity phase and the frequency, even though we bias at a constant current with negligible current variation, even with the variations. So why this variations arises? So here I said that it is exhibiting variations, right? So why these variations arises? It is all due to the variation from the temperature. Maybe if there is a temperature variation, due to which there will be a small spontaneous emission. So the two fundamental noise mechanisms are, so the noise whatever that we get, that is due to the spontaneous emissions. This spontaneous emission that is due to arises due to the temperature variations. Okay, that is one thing, and the other one is electron hole recombination. That is a short one. So those are the two different things. As you all know, the laser diode, it is due to the continuous emission of the photons, right? So whatever the noise that comes out, right, that results from the random intensity fluctuation. So here we say that, as I said, it is continuous emission of these photons, due to which it gets added up to the coherent field and a small field component, which will be in random. The phase will be random. Why random? Because we don't know the temperature. It is not in our hands, right? It is to be. It varies randomly. So this due to this random nature, there will be a variation both in the amplitude as well as the phase in the random manner. So which we call it as a random, that is the relative intensity noise. That is what RIN. So the name relative intensity noise. Basically, it is defined in mean square intensity variation. It is expressed in the terms of the mean square intensity variation current. So the resulting mean square noise current, that is given by IR of square is equal to RIN of R into P into B. B, you know what is R naught, what is P and B. So here R naught stands for the what is the what is called the responsivity here. Yes, R is the responsivity, R naught is the responsivity, P is the average power this thing, and B is the bandwidth here, right? So rin of R naught into P into B. So where RIN, it is measured in dB per hertz, and usually it is expressed in the in dB per hertz, and its value will be ranging from -150 to -158 dB per hertz. So here, then, as your noise decreases, this noise will be decreases as when your injection current, the current that you, it is increases as your noise current increases. The current, the injection current increases, your noise is going to decrease. Decrease. Fine. So next is a reflection effects of RIN. So what is this reflection effects? So as you all know, when the current that is in the lasers, and when the light is going to it is going to emit continuously, some portions of the light gets reflected back. So these optical reflections generated within the systems. So as I was telling you, so in the lasers, due to the emission, the light gets it will be transmitting lights in a continuously, right? Continuously. So out of which a few portion of light or few photons gets reflected back. That's what we can. It is a reflection. These things. So in the previous chapter we discussed about. Huh? That losses, right? So return loss we discussed. That is the return loss. So there is optical reflections. Whatever that is being generated within the system, it needs to be minimized. Yes. Why? We have to take some special precautions. So we need to see that so that we can enhance the signal strength, right? So if we are taking back, or if a portion of the light is getting back, that means you are losing some strength of the signal. If we allow the same signal to continue in the same path as other light, then you are going to enhance the strength, right? So we need to take some measures so that we can minimize that optical reflections. Okay, so with which the signal increases the RIN, that is relative intensity noise, by 10 to 10, 20 dB. So here in this diagram, it is a plot against feedback power ratio versus RIN. So first, let me tell you what is this feedback power ratio. This feedback power ratio, basically it is the amount of optical power that is reflected back to the light output from the source. Is my point? Yeah. So the feedback power is the amount of optical power that is reflected back to the light output from the source. Fine. So this here this diagram shows the effect. So here you can see it will be decreases later on. Like, later on as your feedback power ratio is increasing. Fine. As your feedback power ratio is increasing, and it must be less than minus 60 dB. Minus 60 dB in order to maintain the RIN value between this 150 minus 140 dB. So it should be less than 60 dB so that we can maintain the it in the minus 140 dB per hertz. So in order to obtain the sustained or a better efficiency, we need to maintain under these values. So next comes the limiting conditions. So what are the limiting conditions? So as you all know, we encounter many noises at different stages or different levels. Different levels. For example, here you can see whenever our optical power level is at the receiving end will be low, power will be low. Here, the preamplified noise, it is going to dominate with the system noise. So here we come across, as you all know, the quantum noise, the reflection noise, the carrier to noise ratio. So these are the different noise which is going to dominate our system noise. So we need to minimize that. So those are all the limiting conditions, and it is shown in the table. So which I have not mentioned here. The table is with respect to what is the transmitter value, what is the receiver value, such that okay. Here this basically this figure it shows your carrier to noise as a function of your optical. That is here. Signal graph is plotted against optical power versus the carrier to noise ratio with limiting factors. Here you can see the reflection noise limit is 3. Later on, the quantum noise limit effects, which is a 2 dB. Then later on, after some this thing, some after a power, after some power received power, the preamplified noise limit it is going to be less than 1 dB or nearly to equally. So it is going to drop 1 degree. So here I will mention here. So for low light levels, okay. So here the low range thermal noise is a limiting factor and it causes 2 dB roll off. Here you can see 2 dB roll off in C bar n for each 1 dB drop in received power. So for each drop, it will be 2 dB. So that is what here you can see 2 dB roll off in carrier to noise. So later on, as the light level increases, okay, that is at the intermediate level, quantized that is limiting, and where it will drop 1 dB drop in carrier to noise for every 1 dB decrease in the received optical. So at high received power source noise is dominating factor and it will be constant. Fine. Constant C bar N. Yeah. Fine. Next comes your multi-channel transmission system techniques. So what is this multi-channel transmission techniques? What is multi-channel transmission technique? Can you tell me? What is multi-channel? Hello? I think I am audible.
Sir, multiple light channels.
Hmm. What is that? Hmm? What is multi-channel transmission technique? Huh? Transmitting many signal over a single channel. Okay. Any others? Yes, in the slide itself, you can make out. So you already studied your multi-channel transmission techniques. So there is a single transmission thing where you will be sending many signals. So, for example, what that is what your multiplexing, as one of your friends said, it is you will be till now whatever that we studied it was only with respect to single channel, single signal, not single signal and with a single transmitting over a single channel. That means you are sending only one information. Okay. But now, as you all know, by sending a signal channel, resources will be waste. So what we can do is we group the signals of different frequencies. For here you can see base and signals, they are superimposed F1 to Fn. Those many signals, they are they are superimposed. How they are superimposed? Superimposed electronically. So electronically, uh, all those signals will be superimposed electronically, and they will be processed, and then those signals will be fed. For example, here in the diagram you can see, here we have F1 to Fn signals, each with a different frequencies and carrier frequency, that is the each with different baseband signals F1 to Fn. So that is the information signal. Each information is different. So all those signals are being, what I can say is, combined, or it is superimposed on one another, so that you will form a composite a signal. So here it is a FDM signal, and that signal, it is being given here into the optical transmitter. That means here you will be converting the composite signal, and then you will be converting it. Okay. Then it will be transmitted. At the receiving end, again, all the signals will be, that is, the signals will be in a decomposed state. So you need to separate it into separate frequencies, different frequencies. Then those will be separated at different baseband signals, right? So, for example, for this, then simple example is you will be watching TV, and as in when you require, that means, as you you didn't like the program, which is then you will be changing the channels. It is all just because of what? That means you are getting many signals on a single cable. That is a copper cable, for example. Now they are using what in that example it is being used, but here it's an optical thing. Only thing is that it is converted. For example, if you are watching those things in, for example, if you are using a smart TV, then you will be taking a fiber optic cable, then you will be connecting it. So later on, you will be changing again there. Signal what you are getting, that is converted, right? Somewhere in the same way, here it will be multiplex and demultiplex. So one example is that a cable TV. So you will be changing different channels, right? That is what. So, but all the signals, it will be having its own advantages and its own disadvantages, right? So few methods of multiplexing includes your vestigial sideband amplitude modulation, frequency modulation, subcarrier multiplexing. I think you have heard about these concepts. These concepts have been studied in your digital communication, right? Analog communication with the digital communication you have studied. So I have studied this vestigial sideband modulation, frequency modulation, subcarrier modulation. Have you studied this?
Yes, sir.
Yes. So I need not to tell much you on these things. Next comes your multi-channel amplitude modulation. So it is AM. So this multi-channel AM, the this technique, in this modulation technique, what we did is, it is a oldest one. As you all know, AM was first being used, later on FM being invented and being used. So here you all know that in few applications, the bit rate of the channel is relatively low, but the number of channels are quite large in AM. So that means here it consumes less bandwidth compared to your FM. So which consumes larger bandwidth, whether AM or FM? Which requires a larger bandwidth? FM, yes, very good. So your FM requires a larger bandwidth compared to your AM. So because there the it is going to provide a larger or higher SNR, and it is very less sensitive to source non-linearities. Whereas where AM is very simple, as you all know, AM technique is very simple technique, and it is the primitive one, and it is cost effective too compared to your FM. Fine. So here, typical example is again CATV, that is cable television they have mentioned. So in here, the block diagram, which I have already explained, it is combining n independent channels. All those things will become what is combined, and it is infed, and it is thing. So here, different channels are amplitude modulated on different carrier frequencies. So all these carrier frequencies here, upon which they will be amplitude modulated, then the composite signal will be getting those composite signal will be converting into optical signal, and then will be transmitted. Fine. So the power combiner, it sums up all amplitude modulation carrier producing a composite FDM. So if you are using an FDM, you will be converting that. Okay. So the composite FDM signal, it is used to modulate the intensity of a semiconductor laser directly by adding it to the bias current. So with the variations in the bias current, you will be getting this. Okay. At optical receiver, a band pass filters. Here you will be using a band pass filters as I mentioned here. So in order to separate the individual carriers. So this optical modulation index M. This optical modulation index M, it is given by M equal to summation I equal to 1 to n mi square to the power of 1 by 2. Okay. So, what is this M and what is this MI? MI is per channel modulation index, because all the different channels will not be having the same modulation index, whereas your M is the overall channel index. So, N is the number of channels, whereas MI is the per channel modulation index. Here, as your laser diode, it is non-linear device. As you all know, it is a non-linear device. And whenever multiple carrier frequencies, it passes through such device. So that is the composite signal. And the composite signal is passes through. That means passes through in sense when we convert and it is been said. So the signal will be getting distorted. The signal gets distorted. So the distorted signal, which we call it as the intermodulation distortion, due to the conversion and this thing. So there will be a distortion. So that distortion signal, we call it as intermodulation distortion. Fine. This IMD, it is causes, because as the name itself says, it is intermodulation distortion. So this distortion, it causes the undesirable signals in order to produce the intermodulation product. Okay. So these IMPs are again further they are classified as two-tone IMPs and triple beat IMPs. So here we have two types. Fine. So basically, how they are being classified as a two-tone and a triple tone, it is based upon the frequencies that is going to coincide. Whether two frequencies or three frequencies. Based on that, these are being classified. So here, the triple pair IFS, it is going to be having Fi, Fn, and F minus F T or something like that. So it will be having Fi, Fj, and Fk. Whereas this one, it will be having 2Fi minus Fj in the two channel. So that is a expression is something and moreover it doesn't have any derivation. So that's why I have skipped. So here for any n channel system, it is going to generate n into n minus 1 into n minus 2 by n to triple bit terms compared with n into n minus 1 two tone for your two tone. So it is n into n minus 1 for two tone terms, that is IMPA, and for a triple bit IMPA it is n into n minus 1 minus into n minus 2 by 2. Fine. Okay. Based upon the channel carrier spacing, some of IMPs it falls within the bandwidth, but which is the undesirable. This intermodulation distortion uh, it is going to fall within the bandwidth of the specific channel. And once it falls within the bandwidth, then definitely it's going to affect the signal recovery. So it will be difficult for us to recovery. So this uh, problem we call it as a beat stacking. So beat stacking is nothing but, so whenever your carrier channel spacing, if it falls, if IMPS falls within the bandwidth of this a particular channel, then with which once it falls in within the bandwidth, it is going to affect the signal recovery, and which we call it as a beat stacking. So this beat stacking is going to result with two types of distortion. So what is the two types of distortion? One is composite second order, and the other one is composite triple pair. So composite second order is CSO. As the name itself, it is a second order. So this is P length hyperconium. Sorry, and then this I have taken from some source. So directly I have taken identity. So it is peak carrier power divided by peak power in composite second order IMP. So you make a correction here. It is a peak carrier power divided by that CSO, that is composite second order. It is a ratio of peak power in peak carrier power to the peak power in composite second order. So it is second order. Second order IM term. IM is intermodulation term. Whereas CTB is the peak carrier power divided by peak power in composite third order intermodulation. That is in the second order and the third order. This CSO and this CTO is why we need it. Basically, it is used in order to describe the performance of your multi-channel. So you will be having a n number of channels. So each channel, so you need to it specifies or it describes the performance of the individual channels. Fine. Then this CS1 and CTD, these will be exposed in DBC units. Base DC in DBC, it is going to denote the normalization with respect to the carrier power. So DB with respect to normalization with respect to C, that is the carrier power. Usually this CS2 and CTB, it has to be in the range of minus 60 dBc for a small impact on the system. Both it increases with the increase in modulation index. The CSO and CTB, it is going to increase rapidly with the increase in the modulation index. Fine. Next is multi-channel frequency modulation and subcarrier multiplexing. So this I'll take up in the next class. Any doubts here? Any doubts still here? No. Okay. Fine then. Huh? Thank you then. Thank you all.